Assalamu alaikum everyone. Welcome to our another lecture, continuation of the previous lecture. Our previous lecture was amplitude modulation. We actually started amplitude modulation. So now we already shown that in amplitude modulation the carrier is modulated by the message signal. So we already know the carrier is modulated by the message signal. So we have looked various concept as, so what we covered in the last class as AM modulation. We also have seen the modulation index. We have talked about over modulation. And so on. So today's lecture will be the spectrum of this amplitude modulation. So our lecture is the spectrum of amplitude modulated signal. That's actually our today's lecture. So consider our message signal, which is actually MT. So consider a message signal MT. Consider a message signal MT with spectrum MF, right? We know all this terminology from our previous lectures, Fourier transform. So if this is the case, we draw a typical spectrum of, we can draw the typical spectrum like this. We draw the typical spectrum like this. So this is MF, our message spectrum. This is actually our message spectrum. Where we have frequency FM and frequency minus FM. Frequency FM is the maximum frequency of this message. Maximum frequency of this message. MT. Now let us write our modulated signal XT. Our modulated signal was AC 1 plus KA MT cos 2 pi FCT. Here, this FC is our carrier, right? Carrier frequency. And this Ka is nothing but the sensitivity. Or rewriting it, AC cos 2 pi FCT plus ACKA MT cos 2 pi fct. So k is the our in amplitude modulation. K is the sensitivity. Now the modulated signal, we express it now in two components. This is the one component, this is the another component. Here we can write this cos 2 pi fct as, we can actually express it by the complex form. We can write it cos 2 pi fc equal to probably you know from Euler's equation, right? How we express our complex equation. So for example, this is a real or this is an imaginary part of a signal, and e to the power j theta. For example, this is a complex signal. So this is actually angle theta. So the real part and the imaginary part. So the real part is nothing but the cos j theta, and this is the sine j theta. Sine j theta. Okay. So what we write, e to the power j theta is nothing but cos theta. Sorry, I beg your pardon. This j should not be here. This small j. I beg your pardon. Sine theta and cos theta. So e to the power j theta equal to cos theta plus j sine theta, right? So what is the cos theta? Cos theta nothing but e to the power j theta plus e to the power minus j theta divided by 2. Isn't it? Yes. So cos theta, same thing, e to the power minus j theta will be cos theta minus j sine theta. So if we write, we add this, so it will be like e to the power j theta plus e to the power minus j theta equal to 2 cos theta. So cos theta will be e is amount divided by 2. This 2 comes here. This comes, right? This is how this comes. So we actually express this cos theta in its complex form or complex exponential. The Fourier transform of the complex this exponential, how we express it now. Okay. So we actually express this term, which is actually common in here and also here. That's why actually we convert it, or we express it into complex exponential, so that we can convert it to the impulse in a Fourier transform. Okay. So what we can write, okay, so e to the power, we know e to the power j 2 pi fct. This will be in Fourier transform, how we express it, del f minus fc, right? And e to the power minus j 2 pi fct, this will be expressed as del F plus Fc, right? So our this cos theta, it will be expressed as half of del F minus Fc plus del F plus Fc plus Fc. Now actually we know how to convert or how to represent cos 2 by Fc in a Fourier transform, which is actually this expression, the given by the impulse. Okay, so if I draw this signal in, so we have our modulated signal xt. Our modulated signal have two components. We have seen it. We have two components. Let's draw these two components individually, right? Okay, let's see how they look like. So they will look like this. So our signal, so this is actually the Fourier transform of this cos. We are plotting Fourier transform of AC cos 2 pi Fct, which is one component is actually this one, another component will be this one. So which is actually this one and this one. Here we can see that, or rewriting AC, this one, this whole portion. What will be the whole portion? AC cos 2 pi Fct. We already know this portion, this portion, which is actually this. So it will be expressed at AC by 2, right? Del F minus Fc plus AC by 2 del F plus Fc. These two parts, this part is here and this part is here, where we have the half and this AC comes here. Okay. Okay. So this is actually our okay. This is actually in frequency domain. We are writing in Fourier transform means this is in frequency domain, where we have Fc and minus Fc, and this del, this amplitude is actually AC by 2. This amplitude also AC by 2. So we have drawn thus two individual part. So we can see that our modulated signal can be divided into two component, and this component we express it by this equation, where we have two portion, this portion, and which is actually here, and this portion which is actually here. So we are done with this part. We can see how the spectrum of this component look like. Okay. So this is actually nothing but our carrier component. Carrier component. So this is actually our carrier component. Okay. Now the other portion. Okay. Here this portion. Let us rewrite the other component, which is AC KA MT multiplied by the cos 2 pi FC T. Okay. So this portion we will actually convert it. This is actually in time domain. We will actually convert it to the frequency domain. Okay. So these are actually the constant. So if I convert this to frequency domain, it will look like AC KA MT will be MF. Okay. How this will look like in Fourier transform? In Fourier transform, this will be, you already know this one from here, from this equation, from this portion. From this portion, we know it. How? It is actually nothing but half, which actually this equation, half of del F minus FC plus del F plus FC. Now, what remains? This multiplication remains. So, multiplication in time domain actually convolution in frequency domain. Okay, so we put this note here. So, multiplication in time domain is actually a convolution in frequency domain. Okay, frequency domain. Okay, how we know it? We know it from the Fourier transform. Okay, so if I complete this, so this is Fourier transform happening here. So after Fourier transform, so how it looks like if we multiply the whole term, this term with this sum, then it will be AC KA by 2 MF convolution of del F minus FC plus plus AC KA by 2 MF convolution of del F plus FC. So what we can see here from the properties of delta function, that MF, the spectrum of the message, is shift to the FC. Means this, what it do, it actually shift MF to FC, and the same way what it do is actually shifts MF to minus FC. That's we are actually seeing here. So the MF convolution of del F minus FC simply shifts the spectrum MF to FC and MF convolution of del A plus FC shift the spectrum to minus FC. So from the properties of the delta function, we can check that this is simply shifting of MF either to FC or minus FC. Where this extra portion in each cases, this is nothing but the scaling factor. Okay, so now from the equation we can see that we will going to have two impulse. From this two we will see that there will be two impulse. So let us draw the spectrum of this AM signal. Which one? This one. So our spectrum of AM signal, which was what? Remember at the beginning, 1 plus K A M T multiplied by the AC cos 2 pi FCT. So let's see how this spectrum look like. So you can see that if I draw this one, this two here, this two, what will I have? Okay, so this is actually our so here we can see that this one MF, this part, this part, we can draw like here. So we can draw like this. It's not good. Like this. So one of the spectrum is like this, which is actually, and another one is like this. This kind of like this. Yeah. So this is actually our half AC K A M M F minus FC, which is due to this one, and this will be our half AC K A M F plus FC. We just say that this delta function shift the MF to FC, which is actually this one, and this delta function shift the MF to minus FC, which is actually this one. Okay. Yeah, and from our because we are drawing the complete signal, which is actually have two component, right? So this was one like second component. Actually, this was the second component, and second component, and this was our first component, which is actually so this one. This is our first component. This is our first component. Okay, so from our first component, we also see this spectrum, these two spectrum, right? Let's draw them here. Okay, which will be actually, this one. Which is actually this one, right? which is actually A by 2 del F minus Fc, or A by 2 del F plus Fc. You see, we did it earlier. This is the amplitude, and this was the, like you see, this was the amplitude, and this is the delta component. So this was the amplitude, and this is the delta component. Okay, so that actually we draw here. Okay, so this is Fc, this is minus Fc. So if this is the case, then this is Fc plus Fm. This is our message. So this is actually Fc minus Fm. Same thing. This is minus Fc plus Fm. I mean this one. And this is minus Fc minus Fm. Here, this portion and like this portion is called the lower sideband. These are called the lower sideband or LSB. These two components, this portion, and the other portion, this one, this one, these are called upper sideband. Upper sideband. Upper side band. Okay. Okay. So if in our complete spectrum of this EM signal, these two triangle bands corresponds to the spectrum of the original message shifted to either Fc or minus Fc, and this is the complete spectrum of the amplitude modulated signal. Now look at this. It is symmetrical about the origin. It is symmetrical about this origin, right? And it contains two bands, one shifted on to the positive frequency side and one to the negative, one to the positive and one to the negative side. So here minus F here minus Fc, 2 minus Fc plus Fm. These are the lower sideband. Also same for Fc to Fc minus Fm. These are lower sidebands, and Fc to Fc plus Fm, or F minus Fc to minus Fc minus Fm, they are called the upper sideband or inner sideband, outer sideband, right? Okay, these are very important because they will be used for future modulation. So they are called individually, they are called SSB, single sideband, single sideband, which have both lower sideband and upper sideband. So lower sideband or upper sideband. We can use either of the sideband to modulate the signal, future modulation. So single sideband only use one of the upper or lower, which actually saves lots of energy, which is actually the topics of our feature modulation scheme. So we will not discuss it now. Okay. So we know the complete spectrum of a amplitude modulated signal. So now the detection. So the detection. We say we modulated the signal, we transmit the signal. How to detect it? Detection will obviously will be by envelope detector. Envelope detection, say envelope detection. So how do you do envelope detection? Envelope detection actually what it do? It actually detects the envelope of this amplitude modulated signal. So it detects the envelope of transmitted signal to recover the message. So what to do? Detects envelope of transmitted signal to recover message to the. So and this only works when there is no distortion, when there is no distortion. Why distortion happens? Because of the oversampling. We have seen it earlier. If there is no distortion, then envelope detection works, which actually the mu should be greater than or equal to 1, where mu is the modulation index. So modulation index, right? So let us see how this detector circuit works. Okay, envelope detector. So envelope detector. So this is our envelope circuit. So here the envelope detector circuit look like this. For example, we have a source resistance connected to a amplitude modulated input. So this is actually AM input. AM input, yeah, input signal. Amplitude modulated after modulation, it is passed through this circuit. So this is, it goes through a diode, and there is a capacitor here and a load resistance across this load RL. We actually measure the V out. Very simple circuit. So this is a envelope detector, or is also called a peak detector. Peak detector. So it's how to do it. Detects the peaks of the carrier. The carrier which was modulated, it detects the peak of that carrier. So how it works? Let's see how it works. For example, let me draw a amplitude modulated signal again, just for understanding. When these conditions are fulfilled, means no distortion, mu is less than 1, then for example this is a message. For example, this is a for example this is a message signal. Just a simple modulated. I'm not drawing any during any scaling. Okay. So okay, just I draw a simple carrier, modulated carrier. Here, you see what is our envelope? Where is our envelope? Envelope. Remember, our message signal was 1 plus KAMT, right? And 8AC. So here, this is actually our modulated carrier, right? This is actually our modulated signal. Modulated carrier signal, which is actually our V in input in the circuit, which is actually this one. Here we give us V in. When, so let's say V out, VO, which is actually measured here. VO is the output of the envelope. So output of this envelope detector circuit. Whenever you see V in is rising in amplitude. V in is rising in amplitude. So which actually rising, this voltage is rising, means actually this diode becomes forward bias. Once it forward bias, this capacitor is getting charged. So V in increasing, capacitor is also getting charging. So you see here, our red one is V in and our green one is the V out. Okay. Now, whenever at this point, what happened is the V in, V in is actually getting down here from this portion. Means actually V in is actually decreasing. At this point, at the maximum of this height, the capacitor is charging. And now V in is actually decreasing in value, right? Decreasing in value. We can see it decreasing in value. When it's decreasing in value, what happened? The this voltage is actually decreasing now, and which is actually lower. When it reaches to this point, the diode was forward bias and capacitor actually charges to its maximum, right? When this V in actually decreasing, this V in actually decreasing in value, what happened? This capacitor becomes higher voltage, which makes this diode reverse bias. So capacitor was charging. Now, when the capacitor becomes reverse bias, the diode becomes reverse bias, current cannot go through anymore like this way. What it goes? It actually goes through the resistor. The capacitor is actually losing its energy through the resistor. So losing its energy through the resistor. Again, as soon as these input V in is actually catching up fast, and as soon as it crosses this area, which actually makes this diode again the forward bias, and this capacitor again starts charging. As soon as it reaches the same point, same thing happened. Okay, so it actually again discharging, is again discharging, or is again charging. So it's again discharging, and it's start charging like this. Now, if so, this figure was drawn for illustrative purpose. I make it bigger. For practically, what happened? Practically, this carrier, you see here the carrier frequency is very low. From this point up to the complete cycle to this point is very low. But you remember, this FC must be much higher than FM for this modulation. Means actually it would be much, so it will be much higher frequency instead of our lower one. So if I redraw it here, so it will be much higher. Previous figure was like illustrative purpose. But it's much higher. I mean, I just increase the frequency. So what happened? It go, so yeah, it capacitor charges, discharges, charges, discharges, charges, discharges, charges, discharges, charges. So you see, this is almost following the edges of this, or tip of the carrier, right? So by manipulating this, for example, if you slow the charging of the capacitor, so the slope will be very not that this much sharp, and by very high frequency, they're almost like touching on each tips. This is how this envelope is actually detecting the envelope. Actually, the detector actually in detecting the tip of the carrier, which is actually we call the envelope of the carrier. So we can say, so we can write when amplitude modulated wave or amplitude modulated signal V in is greater than VO, what happens? Two condition, either V in is greater than VO, or V in is less than V. This one, V in is when this charging happening. This was charging. Then what is happening? Diode is in forward bias. So capacitor is charging to pick up the carrier, to pick up the carrier, which is actually this one, to the pick up the carrier. But when EM but when opposite happens, when V in is less than V0, what happened? Diode is reverse bias. So diode is reverse bias, and the capacitor discharges, and the capacitor discharges here. Capacitor actually discharging here. Capacitor discharges through the RL. Through RL. This is the, in our circuit, this is the RL. So through this RL, capacitor actually discharges. So this is actually how the whole stuff works. So envelope detector comprises only of diode, capacitor, and resistor. You see how simple it is, the circuit is. So it is actually diode, it have a diode, it have a capacitor, it has a capacitor, and it also have a resistor. Very simple circuit. So we see it is very simple. So it is very simple, low cost, right? So and used for a very common application like TV or radio receiver, amplitude modulated receiver. Okay. So here ends our this lecture. Assalamu alaikum.